familiar, if you remember, you want to regress y on x bar, where x bar is the true value. But all you have is x, yeah, and x is measured with error. Yeah, it's the true value plus error. Yeah. So if you go to minimize your sum of squares, yeah, you get the effective value of y minus alpha minus beta is x squared. Yeah. So that's what you want to minimize, the sum of square deviations. Differentiate that with respect to alpha. You'll get that the expected error term equals 0. Differentiate this with respect to beta. You'll get the expected error term times x equals 0. So these are known as the normal equations of OLS. You know, they define the alpha and the beta, because you can solve these two equations and you'll get the normal, you'll get the OLS estimates of alpha and beta. The beta equals covariance of y with x over the variance of x, and the alpha equals the mean of y minus the estimated beta times the mean of x. So, yeah, so you'll get the beta equals covariance y with x over the variance of x. But remember, the x equals the true value plus error. So when I replace the x with the true value plus error, I get the right thing on top in the numerator. I get the covariance of y with x bar, that's what I'm after. But on the denominator, I get the variance of x plus the variance of v. Since this is just error, it's actually uncorrelated with x, so there's no covariance. But what I get is a biased estimate of the true beta, right? Because I have this extra jump on the denominator. Yeah? And really that comes about because the x variable is not independent of the error. Yeah? So that's a little bit of revision for you about measurement error. So the solution is to use instrumental variables, and we'll call that Z. So the properties of instrumental variables are they need to be uncorrelated with the error. Yeah, that is, they need to be exogenous. And they need to be relevant, so uncorrelated with the error, but correlated with the true value. Yeah, non-zero correlation. And then the instrumental variable estimator ends up being not covariance y with x over variance of x, but covariance y with z over covariance x with z. Yeah? So z replaces x in the estimation. So let me take you through how you do that. You can think of it as a two-stage procedure. So you regress first your x on your z. So you get a beta of covariance x with z over variance of z. You define the estimator x as being a plus bz. In the second stage, you use that estimator x hat as the new x. You get then that the beta equals covariance y with x hat over the variance of x hat. Filling in what the x is, it's a plus bz. A plus bz, and the b comes out. A is a constant, so there's no covariance. So you get b covariance y with z, b squared, variance of z, because the z's around a variable, a is a constant. So you get b squared variance of z, and the b, one of the b's cancel. So you get covariance y with z over beta variance of z. But up here, remember what the beta was. So now you're going to get cancellation, yeah, of the variance of z. Yeah, and so you're going to end up with covariance y with z over the covariance of x with z. So that's our familiar instrumental variable estimator. Yeah, and you'll have access to all of these slides, so you don't have to follow the map now. But when you go back later, you'll see it's fairly simple now. But here's a better way to think of it, right? You can think of the normal equation for ordinary least squares. That is the error term equals 0, and the error term times the x variable equals 0, which leads to the beta equals covariance y with z over variance of x. However, we know that this x, is measured with error. So in this the system of equations, we're going to replace the x with z, the instrument. Okay. And now, if we solve these two equations simultaneously, we get that the beta equals the instrumental variable estimate, covariance y with z over covariance x with z. So it gives you another way to think of the instrumental variable estimator, and a better way. You know, you don't have to do a two-step procedure. you just write down the normal equations below this. X, we know that X is measured with error, so X and the error term are not, the product of that is not equal to 0. So we need to put in Z, which is correlated with the right X that you want, the X star, but we know it's uncorrelated with the error. So that's why it's important that the instrument has those properties, that it's correlated with the true X and that it's uncorrelated with the error. So a specific example, think about a simultaneous equation. So here we got y1 is a function of y2 and x1 plus error, u1. y2 is a function of y1 and x2 plus error. But look at the first equation. You have y2 in here. But we know from equation 2 that y2 is a function of y1 and x2, but it's also got error. Yeah. So in this simultaneous equation, you've got an x variable, that is the y2, which we know from the system is measured with error. So the simultaneous equation, pops up as having the same sort of problem as measurement error, right? Because the y2 is measured with error. And look at this value of y1 in the second equation. Well, y1 you can see is a function of y2 and x1, but it's also got the u1, the error. So y1 is measured with error. Yeah? And so that's the problem. Yeah? So you end up with biased and inconsistent